Hello, Professor. The presentation is about software behavior-oriented parallelization. Nowadays, there are many applications can be done in parallel fashion so as to accelerate the execution. For example, there are many Linux command utility that can be executed in parallel, such as the compression commands, and some scientific computation work can also be done in parallel. But it's not that easy to parallelize program. The reason is the program may be very complex. For example, there may be bit level operations and unrestricted pointers, and also there may be exception handling statement in the code, which leads to the unexpected jump statement, jump execution. And also in the program, there may be customized memory management. So in order to address the problem, the authors in the paper propose a system called behavior-oriented parallelization, BOP. So the goal of BOP is to improve the execution that contain cause, ground, and possibly input different parallelism. And at the same time, it will guarantee the correctness and the basic efficiency. There are three components of the BOP system. The first is the part for selection of possibly parallel regions called PPR. This can be done by the programmer or by the profiling tools coming with the BOP system. And the second part is a compiler, which can transform the data and the code into machine-level code. And the last part is a runtime system. And the runtime system can guarantee the correctness and the efficiency of the parallel execution. First, let's look at the possibly parallel region, which is called PPR. Here is an example of PPR. In a program, there might be multiple PPR. The PPR region is marked by a beginning marker and ending marker. And the multiple PPR region might be executed in parallel without error. And within the PPR, the system can allow unpredictable entry or exit. So this figure illustrates how the BOP execution model works. First, the left side is a diagram to show the sequential execution of a program, and the right part of the figure shows the BOP execution. Basically, the BOP execution starts with the lead process. It executed sequentially until it encountered a beginning point of a PPR. Once it encounters a beginning point of a PPR, it will fork a new speculation process, and the speculation process jump to the end of the PPR. In this example, is PPR P So, and then the speculation process executed from this point, which is the end of PPRP, and it executed sequentially until it reaches another PPR region. And the same process will be done in the system. That is, the speculation process will fork a new speculation process and then jump to the end of the Q region. And from the end of Q region, it starts execution sequentially. And the leading process should be continue running. It's called understudy execution. And once the lead process reaches the end of region, in this example is region P, it will wait for the speculation process 1 to finish. And once the speculation 1 finishes, it will check if there is a conflict. If not, it will commit the change to speculation 1. You can see this execution model is a recursive process. The overhead of creation of a process of the commit can be hidden because this is a pipelined execution model. In this example, the two speculations are successfully finished, and so the program will take the result of the speculation processes. But if there is an error, of the speculation process, the speculation process will be aborted. The BOP execution model also guarantees the basic efficiency because the whole program, the speed of the whole program is at least as fast as the sequential execution. Here is a summary of the process level parallelization. First, as we saw before, this is a process-based system, so it can provide strong isolation. This is because the operating system naturally provides the isolation of different processes, and since this execution model is pipelined, so most of the overhead can be overlapped, can be hidden within the pipeline execution. And also, because they use understudy execution, this can guarantee the basic efficiency. So, which means at least that the program is as fast as the sequential version execution. A key challenge in such system is how to guarantee the correctness and how to protect the data. The BOP system guarantees that the same result is produced as in the sequential execution if the speculation process succeeds. basically it partitioned the address space of a running program into 3 disjoint groups. They are shared and they are shared data and checked data and private data. For example, for shared data, the lead process will turn off the write permission, and the speculation process will turn off the read permission. And this is protected in page level. And for different kind of data or variables, the BOP system provide different mechanism to guarantee the correctness. And at the same time, there is one thing to mention, that is the overhead of the protection is proportional to the data size rather than the access time. This is a summary or comparison of thread-based system or process-based system which is employed in this paper. Even though the thread-based system is more efficient, but it makes the protection difficult to handle. For example, for a process-based system, there is no need to do the synchronization, but in a thread-based system, there should be a synchronization overhead. And in a process-based system, relaxed dependency can be achieved, but in a thread-based system, this cannot be achieved. And in addition, the thread-based system is kind of optimistic parallelism. Here is the evaluation experiment setting for the system. And here is one of the experiments they conducted. It's a zip compression command program. Basically, they compared the sequential execution and the speculation parallel execution. The speculation depth means how many parallel PPR are marked identified in the system. We can see with increasing number of the PPR, we can gain a speed up increase. This picture shows other program. The result of other program. One is a parser and Xlibs program. The same observation, we can find the same observation here with small parallel PPR regions, which means with more parallelism, there are a more speed up increased. Here is the BOP system compared with the thread-based system and the sequential execution version, and different number of PPR regions. The same result. So with more PPR regions, we can gain more speed up increase. Here is the conclusion. In this paper, they proposed a BOP system which can exploit coarse-grained parallelism, and it provides a strong isolation on process level, and with the cost amortized by pipeline execution, and it can also guarantee a basic efficiency by using the understudy execution sequentially. For a programmer, it's the programmer doesn't need to programming in parallel fashion, because the BOP system can handle all the work, and for the PPR region, it can allow error handling statements inside it, and can allow a garbage collection and hidden dependency, and some abnormal exit and entrance. Thank you.